Late in the morning of April 28, 1958, the USS Boxer aircraft carrier ship was about 70 miles off the coast of the Bikini Atoll in the Pacific Ocean. The crew of the Boxer was preparing to launch a high-altitude helium balloon. In fact, this would be the 17th high-altitude balloon to be launched from the ship. But this one was a little different. Where those first 16 balloons carried some instruments and dummy payloads, attached to this balloon was a 1.7 kiloton nuclear warhead, codenamed Yucca. The ship, balloon, and bomb were all part of Operation Hardtack, a series of nuclear tests conducted by the United States in 1958. Yucca was the first test of a nuclear blast in the upper limits of Earth's atmosphere. About an hour and a half after the balloon was launched, it reached an altitude of 85,000 feet, or 26,000 meters. As two B-36 Peacemaker bombers loaded down with instruments circled the area, the warhead was detonated. Of course, the research team collected all kinds of data during the blast, including the speed of the shockwave, the effect on air pressure, and the magnitude of nuclear radiation released. But from two locations on the ground, they were also measuring the electromagnetic waves resulting from the blast. It had been known since the first nuclear explosions that blasts generate an electromagnetic pulse, or EMP, mainly because it kept frying electronic instruments. But until hardtack, nobody had ever measured the waves generated from a detonation in the upper atmosphere. What they recorded was so far beyond their expectations that it was dismissed as an anomaly for years. All that appears in the report is a casual mention of the estimated electromagnetic field strength at one of the monitoring stations being around 5 times the maximum limit of the instruments. It wasn't until 5 years later that the US physicist Conrad Longmire would propose a theory for electromagnetic pulses from high-altitude nuclear blasts that is still the widely accepted explanation for why they're orders of magnitude stronger than those generated from blasts on the ground. Since then, our fears of nuclear war not only included the scenario of a warhead hitting a populated area, destroying cities and creating nuclear fallout, but also the possibility of one detonating far above our heads in the upper atmosphere, sending a strong enough EMP to disrupt electronic devices and even take out the power grid. As with most weapons, the best and most comprehensive research on EMPs is classified, but in 2019, a coalition of energy organizations and government entities called the Electric Power Research Institute, or EPRI, funded a study to try and understand exactly what could happen to the power grid from a high-altitude nuclear EMP. It's not the only study of its kind, and it's not without criticism from those who think it leans optimistic, but it has the most juicy engineering details from all the research I could find, and the answers are quite a bit different than Hollywood would have you believe. This is a summary of that report, and it's the first in a deep dive series of videos about large-scale threats to the grid. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the impact of a nuclear EMP on our power infrastructure. This video is sponsored by CuriosityStream and Nebula. More on them later. A nuclear detonation is unwelcome in nearly every circumstance. These events are inherently dangerous, and the physics of a blast go way beyond our intuitions. That's especially true in the upper atmosphere, where the detonation interacts with Earth's magnetic field and its atmosphere in some very unique ways to create an electromagnetic pulse. An EMP actually has 3 distinct components, all formed by different physical mechanisms that can have significantly different impacts here on Earth's surface. The first part of an EMP is called E1. This is the extremely fast and intense pulse that immediately follows detonation. The gamma rays released during any nuclear detonation collide with electrons, ionizing atoms and creating a burst of electromagnetic radiation. That's generally bad on its own, but when detonated high in the atmosphere, Earth's magnetic field interacts with those free electrons to produce a significantly stronger electromagnetic pulse than if detonated within the denser air at lower altitudes. The E1 pulse comes and goes within a few nanoseconds, and the energy is somewhat jokingly referred to as DC to daylight, meaning it's spread across a huge part of the electromagnetic spectrum. The E1 pulse generally reaches anywhere within a line of sight of the detonation, and for a high-altitude burst, this can cover an enormous area of land. At the height of the Yucca test, that's a circle with an area larger than Texas. A weapon at 200 kilometers in altitude could impact a significant fraction of North America, but not everywhere within that circle experiences the strongest fields. In general, the further from the blast you are, the lower the amplitude of the EMP. But because of Earth's magnetic field, the maximum amplitude occurs a little bit south of ground zero in the northern hemisphere, creating this pattern called a smile diagram. But no one will be smiling to find out that they're within the affected area of a high-altitude nuclear blast. Although a weapon like this wouldn't damage buildings, create nuclear fallout, be felt by humans, or probably even visible to most, that E1 pulse can have a huge effect on electronic devices. You're probably familiar with antennas that convert radio signals into voltage and current within a conductor. Well, for a strong enough pulse spread across a huge range of frequencies, essentially any metallic object will act like an antenna, converting the pulse into massive voltage spikes that can overwhelm digital devices. And the E1 pulse happens so quickly that even devices meant to protect against surges may not be effective. Of course, with just about everything having embedded electronics these days, this has far-reaching implications. But on the grid, there are really only a few places where an E1 pulse is a major concern. The first is with the control systems within power plants themselves. The second is communication systems used to monitor and record data to assist grid operators. The EPRI report focused primarily on the third hazard associated with an E1 pulse, digital protective relays. Most folks have seen the breakers that protect circuits in your house. The electrical grid has similar equipment used to protect transmission lines and transformers in the event of a short circuit or fault. But unlike the breakers in your house that do both the sensing for trouble and the circuit breaking all in one device, those roles are separate on the grid. The physical disconnecting of a circuit under load is done by large, motor-controlled contactors quenched in oil or dielectric gas to prevent the formation of arcs. And the devices that monitor voltage and current for problems and tell the breakers when to fire are called relays. They're normally located in a small building in a substation to protect them from weather. That's because most relays these days are digital equipment, full of circuit boards, screens, and microelectronics. And all those components are particularly susceptible to electromagnetic interference. In fact, most countries have strict regulations about the strength and frequency of electromagnetic radiation you can foist upon the airwaves, rules that I hope I'm not breaking with this device. This is a pulse generator I bought off eBay just to demonstrate the weird effects that electromagnetic radiation can have on electronics. It just outputs a 50 megahertz wave through this antenna, and you can see when I turn it on near this cheap multimeter, it has some strange effects. The reading on the display gets erratic, and sometimes I can get the backlight to turn on. You can also see the two different types of E1 vulnerabilities here. An EMP can couple to the wires that serve as inputs to the device, and an EMP can radiate the equipment directly. In both cases, this little device wasn't strong enough to cause permanent damage to the electronics, but hopefully it helps you imagine what's possible when high-strength fields are applied to sensitive electronic devices. The EPRI report actually subjected digital relays to strong EMPs to see what the effects would be. They used a Marx generator, which is a voltage multiplying circuit, so I decided to try it myself. A Marx generator stores electricity in these capacitors as they charge in parallel. When triggered, the spark gaps connect all the capacitors in series to generate very high voltages, upwards of 80 or 90 kilovolts in my case. My fellow YouTube engineer, Electroboom, has built one of these on his channel if you want to learn more about them.
There we go. It is still pretty big.
Mine generates a high voltage spark when triggered by the screwdriver. Don't try this at home, by the way. I didn't design an antenna to convert this high voltage pulse into an EMP, but I did try a direct injection test. This cheap digital picture frame didn't stand a chance. Just to clarify, this is in no way a scientific test. It's just a fun demonstration to give you an idea of what an E1 pulse might be capable of. The E2 pulse is slower than E1 because it's generated in a totally different way, this time from the interaction of gamma rays and neutrons. It turns out that an E2 pulse is roughly comparable to a lightning strike. In fact, many lightning strikes are more powerful than those that could be generated by high-altitude nuclear detonations. Of course, the grid's not entirely immune to lightning, but we do use lots of lightning protection technology. Most equipment on the grid is already hardened against some high voltage pulses, such that lightning strikes don't usually create much damage. So the E2 pulse isn't as threatening to our power infrastructure, especially compared to E1 and E3. The final component of an EMP, called E3, is again much different than the other two. It's really not even a pulse at all because it's generated in an entirely different way. When a nuclear detonation happens in the upper atmosphere, Earth's magnetic field is disturbed and distorted. As the blast dissipates, the magnetic field slowly returns to its original state over the course of a few minutes. This is similar to what happens when a geomagnetic storm on the sun disrupts Earth's gravity, and large solar events could potentially be a bigger threat than a nuclear EMP to the grid. In both cases, it's because of the disturbance and movement of Earth's magnetic field. You probably know what happens when you move a magnetic field through a conductor. You generate a current. We call that coupling, and it's essentially how antennas work. And in fact, antennas work best when their size matches the size of the electromagnetic waves.
For example, AM radio uses frequencies down to 540 kilohertz. That corresponds to wavelengths that can be upwards of 1,800 feet or 550 meters. Big waves. Rather than serving as a place to mount antennas like FM radio or cell towers, AM radio towers are the antenna. The entire metal structure is energized. You can often tell an AM tower by looking at the bottom because they sit atop a small ceramic insulator that electrically separates them from the ground. As you can imagine, the longer the wavelength, the larger an antenna has to be to couple well with the electromagnetic radiation. And hopefully you see what I'm getting at. Electrical transmission and distribution lines often run for miles, making them the ideal place for an E3 pulse to couple and generate current. Here's why that's a problem. All along the grid, we use transformers to change the voltage of electricity. On the transmission side, we increase the voltage to reduce losses in the lines, and on the distribution side, we lower the voltage back down to make it safer for customers to use in their houses and buildings. Those transformers work using electromagnetic fields. One coil of wire generates a magnetic field that passes through a core to induce current to flow through an adjacent coil. In fact, the main reason we use alternating current on the grid is because it allows us to use these really simple devices to step voltage up or down. Up to a certain point, most materials used for transformer cores have a linear relationship between how much current flows and the strength of the resulting magnetic field. But this relationship breaks down at the saturation point, beyond which additional current won't create much further magnetism to drive current on the secondary winding. An E3 pulse can induce a roughly DC flow of current through the transmission lines. So you have DC on top of AC, which creates a bias in the sine wave. If there's too much DC current, the transformer core might saturate when current moves in one direction but not the other, distorting the output waveform. That can lead to hot spots in the transformer core, damage to devices connected to the grid that expect a nice sinusoidal voltage pattern, and lots of other funky stuff. So what are the implications of all this? For the E1 pulse damaging some relays, that's probably not a big deal. There are often redundant paths for current to flow in the transmission system. That's why it's called the grid. But the more equipment that goes offline and the greater the stress on the remaining lines, the greater the likelihood of a cascading failure or total collapse. EPRI did tests simulating a 1 megaton bomb detonated at 200 kilometers in altitude. They estimated that about 5% of transmission lines could have a relay that gets damaged or disrupted by the resulting EMP. That alone probably isn't enough to cause a large-scale blackout of the power grid, but don't forget about E3. EPRI found that the third part of an EMP could lead to regional blackouts encompassing multiple states because of transformer core saturation and imbalances between supply and demand of electricity. Their modeling didn't lead to widespread damage to the actual transformers, and that's a good thing because power transformers are large, expensive devices that are hard to replace, and most utilities don't keep many spares sitting around. All that being said, their report isn't without criticism, and many believe that an EMP could result in far more damage to electric power infrastructure. When you combine the effects of the E1 pulse and the E3 pulse, it's not hard to imagine how the grid could be seriously disabled.
It's also easy to see how even if the real damages to equipment aren't that significant, the widespread nature of an EMP, plus its potential impacts on other systems like computers and telecommunications, has the potential to frustrate the process of getting things back online. A multi-day, multi-week, or even multi-month blackout isn't out of the question in the worst-case scenario. It's probably not going to cause a Hollywood-style return to the Stone Age for humanity, but it is certainly capable of causing a major disruption to our daily lives. We'll explore what that means in a future video. But if you have trouble waiting for the next practical engineering video, you should know that they go live on Nebula before hitting YouTube, and you can watch them without any ads. If you haven't heard about Nebula by now, it's a streaming service built by creators that uses a different model than YouTube. Instead of being supported by ads, you just pay a small subscription fee. That sounds like a small difference, but the result is a huge distinction in content, including videos that don't work well on YouTube and lots of original series from your favorite creators like Wendover Productions and Real Engineering. And we're super excited to continue our partnership with CuriosityStream, a service with thousands of big-budget documentaries on pretty much every subject you can imagine. CuriosityStream loves independent creators, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know it's a little hard to keep track of all the streaming services out there right now, but this bundle is so cheap that you barely have to even consider it. You pay one time, $15 to get an entire year of access to CuriosityStream, plus you get a free year of access to Nebula too. If you're looking for more about the power grid, the How Cities Work series on CuriosityStream has a whole 50-minute episode dedicated to just that. Or catch Sam from Wendover Productions traveling around the world in his hit game show series Jet Lag on Nebula. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think.